Some of your Telegram. Okay. Yes, it's 12 p.m. so let's start. Hi everyone, welcome to CS2105 tutorial 14. I hope you are in the right class. If you are not, feel free also to learn more about networks. So maybe I'll introduce a bit about myself. My name is Jason Christopher. You can call me Jason. I am currently my third year studying computer science. I enjoy swimming, I enjoy reading. Initially not really enjoying coding, but you have to do what you love lah. So I hope it's not my mistake to put this as my hobby, I guess. So I enjoy Indomie. And if you have any J-rock, J-pop recommendations, please let me know. I need to update my playlist soon. And obviously I dislike the bell curve. So yeah, that's about me. So I guess let's do a very quick round of self-introductions. Maybe if you can share me what your name, your major, your year, and also if you have any expectations for this module. And if you have any fun facts, optional lah. Okay? You can start from you in front.
Okay, so I'm Yong Rong, year 1 in Bachelor's of Information Security. Then expectations, I guess, just to learn more about networking. Yeah.
Nice to meet you. Year 1.
Yeah.
Okay.
Same.
Same too. Okay. Next.
So my name is Edmund. I'm also year 1 sem 2 infosec, and then expectation for module not really not much expectation because I see it like quite high level.
Actually, I think this is one of the easier 2K mods that I've taken. I think.
Like quite abstract. Quite abstract.
I thought this one is actually less abstract. Yeah, I've taken 2100 to 2109 except 2104 and 2108. I think this is more of the concrete side actually. Yeah.
Wow, my name is Jason. I'm year 1, information security. Want to learn more about network.
Okay, then maybe Tom.
My name is Tom. I'm a computer science major in year 1. So my expectations for the module is to basically just have a general overview of what networking is.
That's a great expectation. Thanks.
My name is Xavier, year 1, sem 2, infosec major. Expectation for this module is to learn more about networking.
Okay, sorry, Xavier Lee or Xavier O? Xavier Lee. We have 2 Xaviers here. Okay.
Hi, I'm Lauren. Year 2 CS. I guess my expectation was to learn more about networking.
Okay.
Hello everyone, I'm Abhishek, you can call me Avi. I'm year 4 CS, and for me this was just to fulfill my CS break.
Great decision, great decision. Nice to meet you, Avi.
My name is Siddharth, I'm also year 4.
Also same reason? No?
Yes.
Okay. Ayo. Okay. Okay, nice to meet you, Chin Feng.
I'm Gerald, year 2 CS. My expectation is to learn more about network. To pass.
Okay.
I'm Shihui, year 4 CS. I also year 1.
是会单是会 Okay. So we have the first half in front is the year 1s. Then the last half is like the year 4s who need to graduate. Okay. Okay. It's quite a diverse polarity. Thank you, Jody. Next. Oh. Oh, Kuei. Okay. Nice to meet you again. I think the next person. Nice to meet you, Brian. Oh, okay. Interesting. So maybe you can share a bit on what you meant by remember what you learned before.
I was in poly, then I took networking.
Oh,
Yeah, I
okay.
forget everything. So I hope you can retain.
Yeah, I think like most networking courses is like similar lah. We talk about delays, UDP, TCP, transport protocols, how the link works. So I think hopefully this will refresh your memory. lah.
Yeah.
Okay, next. He Jin. Okay, nice to meet you, He Jin. Same reason. Okay. Is this a year 4 thing? Xavier, oh, okay. It's not a pass. Why is the year 2, year 3 so depressing, you know? The year 4 is like, okay, I want to graduate. The year 1 is like, I want to learn. Then the year 2 is like, I passed can already. Okay, nice to meet you, another Xavier. Ayo. Finally,
year 2 ISE, year minor, looking to pass.
sorry, what's your name again?
Chuan Hao,
Xuan Hao.
the call.
Which one? Hao? Quanzhou. Xuan Hao. Eh? Can you say your full name? Sorry.
Wang Chuan Hao, WAN Hao.
Wang Qian Hao. Are you in tutorial 14? 1-4?
I mean, your
Oh, you're in tutorial 15 ah. Okay, I'll just write the name first. Qian Hao with an Q?
yes.
Okay. Okay, I'll tell the next tutor lah. Okay. Okay. So if you haven't done so, please join the Telegram group. I think most of you have joined already. Although the class size is 23 people and we are missing 4 people today. So yeah, please join the tutorial group. For Chen Hao, this might not be tutorial 15, so you can check later. But if you want to join, feel free. Give another 5-10 seconds. So this group will be used for me to send any announcements. I hate Canvas announcements. So yep, please do so. If you can't scan the QR code, I also send the link on Canvas announcements. You can check later. Okay. Now, so attendance and participation is graded in CS2105. This will make up 5% of your module grade. Although the weightage between how much is allocated for attending and how much is allocated for participation, this one is still, we are waiting discussion with the lecturers. However, I will take note of any questions you answer. If you ask any questions, that will also count as participating. And yeah, of course, this will count under the participation side lah. However, this is a very important item to note. Unfortunately, I'm quite bad at recognizing faces. So this is why I bring some papers here. Technically, these are what I used before for my module, so eco-friendly, I guess. So please put your name placard at all times in front. Some people, right, they put the names so they face themselves. I don't know who they are. Yeah, so make sure that you put there so I know who you are. But if I don't know, I always ask your name also later on. You'll see. Okay, any questions so far? For those who just joined, can sit maybe forward. I have, I'm short-sighted, so better so that I can see your name. I also don't like the venue, it's so hard to see people's names here. Okay, so you can contact me through my email or my Telegram. Both of them I'm actually quite active, I check them quite frequently. And if you want to book any consultation with me, please feel free to fill in this link, or you can also click the link there. This is basically for my schedule. So once you book, please let me know via Telegram because I don't receive notifications for this. There was one time that I taught a class before. Someone booked a consultation with me, right? I didn't know. Then I was like, when I went to FairPrice, I go to NTUC, I saw my Google Calendar suddenly 30 minutes to consultation. I'm like, wow. Because they don't notify me one. It just put on my calendar. So please let me know afterwards. Okay? Then if you have any feedback, if you have any suggestions for improvements at any time, I will be opening this form every single week, once a week. So feel free to write any feedback you want since I'll be your tutor for 10 more sessions. So this will be really good for us to adjust expectations also. Okay? Any questions?
Will you send us the slide?
Yes. Yes. Okay? Questions? No. Okay, then we'll start the tutorial today. So this tutorial will be talking about the packet delays, the delays when you send packets from one point to another, as well as what a packet is actually about. Okay? So what is a packet? A packet is actually what we call the fundamental unit of data, because this is like the smallest size that we actually send over a network. Okay? So say for example you have a large file. To better manage this, we will actually split them into smaller chunks that we can manage. So this smaller chunks is basically your packet. Now, when we talk about network delays, there are 4 kinds of delays. And y'all mentioned, or maybe before that, let's just have some consensus here. Do y'all want to volunteer to answer, or do you want me to point someone to answer? Who wants to volunteer? Who prefers volunteering? Who prefers me pointing? How about the rest? Hey, I don't mark your participation. Okay, I guess what if we just like say I'll open the floor first. If anyone wants to answer, then if no one, then I point up. Okay, especially those who haven't participated, likely to get pointed later. Okay, yeah. So we have 4 kinds of delays. Anyone can mention? Okay, propagation delay, transmission delay. What else? Processing delay. One more.
Queuing delay.
Queuing delay. You are Lauren. Okay. Yeah. Okay, so we have processing delay, queuing delay, transmission delay, propagation delay. Easy terms, right? Now, what is a transmission delay?
When the packet moves from the switch to the line, transmission line.
Okay, yeah, when the packet moves from the node itself into the transmission line, right?
Yeah.
How is this different from propagation?
Propagation
Yeah. So what's your name? Stefan. Okay. Have you taken the paper from the front?
No.
Please feel free. Those who haven't taken, please take. Okay. Yeah. So let me just give a very small analogy here. Suppose that here you are an OG leader, right? Your OG is of 200 people. Okay? Quite large OG. So this is you. Now in front of you, say you want to bring your OG to COM3. Then suddenly you have in front of you some business people bringing their OG also to COM lah. Because COM2 bus stop is not there, right? Okay? So these two will fight for D1. But they come first before you. So of course, whoever is here, they will be the first one to get priority on the bus. Okay? So you have to wait for all the other OGs here to board the bus. Now when they board the bus, the next bus comes. One bus can only hold 50 people. The bus comes usually every like 5 to 10 minutes. Okay? Before your OG can board the bus, as an OG leader, you have to be able to manage whether all your team is there. You do a head count. Okay? Then afterwards, you allow them to board the bus. But one bus only 50 people, ma. You have 200 people. Okay? So you have to wait for the next bus until once you actually reach there, you go to COM3. This is actually illustrating the 4 kinds of delays here. First one, when the other OG, when you wait for them to actually leave, that's your queuing delay. Once no one is in front, you do a head count, see if anyone is still missing, then that's your processing delay. But the bus comes intermittently. Not everyone can board the bus at the same time. So to actually hit the road, okay, that is your transmission delay. Then when you move from U-town to COM3, that is your propagation delay. Okay? So I hope this will clarify between transmission and propagation. Any questions so far?
The processing delay and queuing delay, are they like interchangeable in terms of their order? Because in the lecture it was processing then queuing first.
Yeah, they might be interchangeable, depends on how you actually consider them. Yeah, so some of them would want to check before you enter the queue, right? Some of them, for example, they might just go into the queue first, then they just directly check before they send. So, might be interchangeable. But as long as the entire delay is an addition process, so should not be dependent on that. It's commutative anyways. Okay? Yeah.
But why would the processing delay be additive to queuing delay if it's done? Like it can be done while it's in the queue. Why would it be addition if it comes first?
The thing here is the thing here is also like queuing delay might also be, for example, if the processing delay comes after, right? Then whatever time it takes to process the packets in front of you, that also will be counted as part of the current queuing delay. Yeah. So processing delay is just to process that file. Queuing delay is to wait for the other files in front, for example. Okay. Now say if you want to send 1 bit of data from NUS to NTU, then the time it takes for this signal to move from one point to another, that is your propagation delay. So first question, given that the holes are separated by m meters, then the speed of the propagation is s meters per second. Can we determine the propagation delay in terms of m and s? Anyone? M divided by s. Yep, that's correct. So this one is just a physics problem, right? Speed equals distance over time. So just divide the distance, m, divided by the speed, which is s. Okay, then you should get. Any questions? Okay, if no questions, now say if I want to send like 10 megabyte of file from NUS to NTU, but unfortunately your connection cannot hold say 10 megabytes, can only hold like 1 byte of data. Then if it can only hold 1 byte of data per second, then it will take 10 megabyte over 1 byte per second, right? That will give you how much time you need to send. Okay, so this will depend on the bandwidth of the connection. The amount of data that you can send at one single point in time, that is your transmission rate. Just the amount of data to push itself into the network, not to travel. It's just to put it inside the link. You see the link so small, but the data is quite big, right? So to push it inside the link, that is your transmission rate. So since we have a transmission rate, then the delay caused by actually pushing them into the link, that is your transmission delay. Thus, if you have a single link that is rate r bits per second, and you have a packet of size L bits, what is the transmission time difference in terms of L and R? Those who haven't spoken? Still easy problems, you go later, problems more harder, yes? LR, yes, that is correct. What do you do with LR? What's the operation there? L times R? It's not L times R? It's L divided by R, exactly. Okay. If LR is just the letters, but yeah. So it's like, for example, you have a pitcher which has L liters. The tap only allows R liters per second. Then of course you divide that. Okay? So transmission delay is equal to the size of the packet divided by the transmission rate. That is L over R. Okay?
I have that as myself. I don't like fully get it because I thought if you divide, then it's like the speed at which it goes out, not like the actual delay. Because like if you use a picture example, right, it's just the speed at which the water like come out.
No, the R itself, the speed.
Is it like how much?
So I guess let's try to define what a transmission rate is actually about. So transmission rate is equivalent to saying, transmission rate, which is your R, right, is equal to how many bits of data can you send per some time. Okay, so for example, if your transmission rate is say 50 bits per 1 second, that means every second you can only send 50 bits. Okay, if I represent this as like the L, this is as like the time it takes to send. So then you have this equation. The rate is equal to how many amounts of data can be sent for how many amount of time. So if I want to get this time, then cross multiply, D equals to L over R. Yeah. Say you have like 10 liters of water. You pour it out every second, this will pour out 2 liters. Then by the 5th second, all 10 liters should be up, right? Yeah, so it's just manipulating the equation. Okay.
Can I ask a question? Would this mod always do in bits per second?
You will be surprised there were questions about microseconds also. Yeah. So I guess this is a good time also to share. Usually the mod, right, the midterm and finals are actually not that hard. It's tricky. So I have to read carefully. Okay? Because there was one question that like in the midterm, like among the questions I got it wrong, right? It's because I read microseconds as milliseconds. So it's not always bits per second, but what you can ensure, right, is every time you see this BPS, this should refer to bit per second. If it's not BPS, then it's not. Okay? Okay. So back to this example, if it happens to process the data before transmission, then that's processing delay. If there's someone in front, the time it takes for the people in front of you to get transmitted, then that is the queuing delay. Okay? Just for them to get transmitted. For them to actually board the bus, that is your queuing delay. Now, ignoring processing and queuing delays. Can someone give me the expression for the end-to-end delay? Exactly. So this would just be dtrans plus dprop. Okay, that's your end-to-end delay. Any questions?
The slide was saying that end-to-end like transmission delay must times 2. L over R times 2. Yeah.
What condition will that be?
I don't know, the slides was saying that to calculate end-to-end transmission delay, you take d trans times 2. So I was thinking end-to-end you know.
Because it goes back, then come back. Like, you need a response, right?
End-to-end delay is different from the round trip time. End-to-end is just from A to B. Round trip time is from A to B to A. Yeah. So it's two different things.
I find the slide later then.
Okay.
Yeah.
Okay. Now, suppose host A begins to transmit the packet at time t equals 0. Now suppose that we know the transmission delay. At time is equal to d trans, which is the transmission delay. Where is the last bit of the packet? Abi?
No, I'm just.
Anyone?
Is it not sent out yet?
Not sent out yet?
Yeah.
Any other answers?
The last bit is being pushed.
Okay, so let's see, right? Say, for example, you start here. Until time is equal to your transmission delay, then that is when the last bit just leaves the host A.
So it's not when it just start.
It just like that very tiny delta when it just being pushed up. That's the last time. So if you have a stopwatch, right? You have a stopwatch, 8 people try to run until the last person starts running, then the stopwatch stops. That's the transmission delay end.
I thought it would be like relative to like the first.
When the first one leaves, it starts. When the last one leaves there, it stops the time. Right? So say for example so say for example if I have a stopwatch, right? Now I start. Ding, I start. Dang, 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 until the moment I stop the stopwatch is when this last bit, I stop. That is your time is equal to d trans. Okay? So at time equals d trans, the last bit just leaves. Hey, what's your name? Gerald, okay. Any questions? Okay. Now suppose that the propagation delay is greater than the transmission delay. When time is equal to d trans, where is the first bit of the packet? If the propagation is larger than the transmission delay. Two options. Is it still in the link or has it arrived? Benedict? Still in the link. Okay. Yeah. So this will still be in the link lah. Say for example here my transmission delay is 4 seconds, but my propagation delay is much larger. Then obviously this first bit will still be caught in the link. Now, I think this is a free answer lah. What happens if the d prop is less than d trans? Yeah, then it will just arrive already. Okay? And what's your name? Shi Hui. Okay. Yeah. Any questions so far? Now, suppose we have an S, which is your propagation speed, 2.5 times 10 raised to 8, L, the packet size, 120 bits, and R, the transmission rate, which is 56 kilobit per second. We want to find a distance M such that the propagation delay is equal to the transmission delay. Has anyone counted this and would like to share the answer? It's quite a large number.
535714.
535714. Yeah, I think that should be correct. Yes. So how did you get 535714? L over lambda s. Yeah, that's correct. So here you have the propagation speed. You want to find the certain m such that this equation holds, right? So we write this equation. Then we substitute propagation delay is equal to m over s. Question 1a. Transmission delay is L over R. Question 1b. Substitute the values. Then you get your m is equal to, cross multiply this 120 bits times 2.5 times 10 raised to 8 divided by this 56 kilobit per second. Then you should get 535714. Okay? Any questions? Clear on this? I think this is like some high school problem kind of stuff lah. Okay? Now, that is your first question. Now we move on to question 2. So a packet switch receives a packet and determines the outbound link to which the packet should be forwarded. Now in this scenario, when the packet arrives, there's one other packet that is halfway done being transmitted. So something like this. This is you here, the packet. In front of you, you have several packets, 4 other packets waiting to be transmitted. One other packet is halfway done being transmitted. Okay? Suppose that all these packets are 1500 bytes. Link rate is 2 megabit per second. What is the queuing delay? If you don't have the answer, you can tell me how to compute also. 0.0? Yeah, that is correct, yeah. How did you get 0.027?
It's 12,000 bits. And then essentially you have to wait for 4.5
Mm.
12,000 bits to be transmitted first. So you wait for that long. And then you divide by the link rate.
Yeah, that sounds correct. What's your name? He okay. Okay, yeah, what He mentions is correct. So here you have 4 packets waiting to be sent. One packet is halfway done. So this is like 0.5 packet that is waiting to be sent. Okay? So there's 4.5 packets in queue. 4.5 times 1500 bytes, that is your 6750 bytes. However, as what He mentioned, I will mention this quite a number of times later on. Bytes and bits are 2 different things. This is the common trap in most questions. Okay? Be careful when you read bytes versus bits. So in this case, your bytes has to be converted first into 54,000 bits. That is your 4.5 different packets. Now once you get the number of bits, just divide this by the transmission rate, you will get 27 milliseconds or 0.027 seconds. So usually when the number is like quite when the number itself is quite small, we usually write it in terms of milliseconds. It's easier to see also. Any questions?
Usually the M, right, is 10 to the power 6, right? But then I know some will treat it as like 2 power, 30, yeah, so.
The 2 power thing is more of a security thing. 2107 will teach you using the 2 powers. But for here, we treat it as the 10 power.
Okay.
Yeah. Because the 2 powers is actually what we call the megabits, I think. That's the, when you consider the 1024 thing. Yeah. But for this, for 2105, we assume using the power of 10, unless stated otherwise. Okay. Questions? No. Okay. Now, just now we use numbers. We use 1500 bits per packet. Then we have a transmission rate. We have how many of the packets has been sent. Now we change all of these into variables. Suppose that we have each packet of length L, transmission rate is R, then from the currently transmitted packet, X bits has already been sent. The question is, what's the queuing delay in terms of N, L, R, and X? So N here is just for these packets that hasn't been sent. This currently transmitted packet is not part of the N1. I think the wording of the question is a bit sus.
N times L plus L minus X, then everything divided by R.
N times what? Plus?
Plus L minus X 1 halfway through, then divided by the transmission rate R.
Yeah, that is correct. So this thing, you have N packets waiting to be sent. X bits has already been sent from the current packet. So the remaining items to be sent from the current packet is just L minus X bits. Plus there is this thing, your N packets, each of them L bits, so N times L, that will give you N times L. Okay? So with what Xavier mentioned, Xavier, right? Okay, that will be number of bits to transmit, which is N L plus L minus X. Divide this by the transmission rate R, you will get this equation. This formula, sorry. Okay, any questions? Clear on this? Okay, then I'll move on. Question 3. Now, we are going to introduce something called a message segmentation, which is how we can try to segment the packets into smaller chunks in a sense. Okay? So, consider a message that is 8 times 10 raised to 6 bits long. We want to send this from the source to the destination. Okay? Without using message segmentation, how long does it take to move from the source host to the first packet switch? From host just to the first packet switch.
4 seconds.
Hmm?
4 seconds.
4 seconds. How did you get 4 seconds? Yeah, that is correct. So just divide the packet size, divide by the transmission rate, that is 4 seconds. What's your name? Imi. Okay, Imi. Okay, thank you. Any questions on this? No? Okay, now the fun part. How much time do you need to move from the source host to the destination host with 2 packet switches? We ignore propagation delay just now. Who says it's 4 seconds also? Okay, so no one says it's 4 seconds. How much? Why is it 12?
Because it's 4 times.
Because it's 4 times 3. Yes, that's correct. So, because of this thing called the store and forward mechanism, before the first bit can be sent from one switch to another, you have to ensure that the last bit arrives first. Okay? So something like this, say if I simplify this to like just 4 bits of data to visualize, right? This first bit arrives at the first packet switch. But this cannot directly flow to the next one. It has to wait until the last bit arrives, then you can start moving it again. Okay? This is what you call the store and forward mechanism. So one thing is 4 seconds, since the link rate is the same, right? And we ignore propagation delay, all this is contributing to 4 second, 4 second, 4 second, total of 12 seconds. That is to send from the source to the destination. Questions? No? Now, we consider that if we try to segment it into 800 different packets, each packet is now 10,000 bits long. How long does it take to move the first packet from the source host to the first switch? I think this one I'll just skim through. It's quite easy. Transmission delay also, 10,000 bits divided by 2 times 10 raised to 6 bit per second. That is 5 milliseconds.
Wait, so it's 0.005 seconds.
Yes,
Or
milliseconds or yeah. Okay. Now the important part. Sorry, not the important part yet. So when the first packet is being sent from the first switch to the second switch, the second packet is also being sent from the source to the first switch. Okay? So you can imagine it when this packet starts moving here, the second packet will start also moving. Okay, so it's like continuous sliding window kind of stuff. Okay? Yeah. So at what time will the second packet be fully received at the first switch? Just now we counted the transmission delay is 5 milliseconds per packet, right?
15.
15? Why is it 15?
0, then 1, 2, 3. So it's.
Under the first switch.
When the second packet just goes.
Then it's 10.
10, yeah. So time 0, all the packets are in the host. Time 5 milliseconds, this one arrives at the first switch. So add another 5 seconds, 5 milliseconds, then this will arrive at the second packet will arrive at switch 1. Okay? Now, this is the important question. How long does it take to move the entire file, the 800 packets, if you use message segmentation? How long does it take to move 800 packets from the source to the destination? This one might be it might not be a very good number. Anyone? Anyone? Those who haven't spoken, we have Brian, Quay, Chikwan, Kiwei,
So you have 800 packets.
Ivor. I don't think he's here. She's here. Yeah, Quay. How do you get 4.01? 5 millisecond times 802. How did you get 802?
800. The first thing arrived at the destination is 10 minutes.
10 milliseconds? Okay. Actually, this one might be slightly incorrect.
In the count got
But the answer is correct. But yeah. Okay, let me share a bit, right? So so you see here that at 10 millisecond, right? The first packet only arrives at switch 2. Okay? So when it actually arrives in the destination host, you have to add 5 milliseconds. So at time equals 15 millisecond, the first packet arrives. Okay, so this part here, this should have been 15. Okay. However, we see here, for the second packet to arrive, what time? What time will the second packet arrive at the destination? Then you have another 5 millisecond, right? Okay, so if I move 5 milliseconds again, I will see that the second packet will arrive at the destination. Thus, the time it takes now is first packet arrive 15 milliseconds. Second packet, this is plus 5. So any subsequent packets, right, this will arrive every 5 milliseconds. So every 5 milliseconds, I can expect that another packet arrives. So time should be first packet arrived is 15 milliseconds, plus you wait for the remaining 799 other packets until the 800 packet arrive. Each of them is 5 milliseconds each. So this should have been 5 times 799 plus 15. Then this will give you 4.01 seconds. Yeah. So yeah, the method might be slightly different, but actually I will show also that I have this current method also, the 10 millisecond, which I will show later. Okay. So time is 15 milliseconds for the first packet plus 5 milliseconds for each of the remaining packets, 799 packets. That is 4010 milliseconds. Okay. Another way that I think, oh, this one is first bit. Yeah, first bit is 10 milliseconds. Yeah, correct. Yeah, first bit. Yeah, another way to think of it is, I think this is what Kuei method. So I think what Kuei was mentioning was this is the time for the first bit to arrive, right? This is a 10 millisecond. Then you consider 800 times 5. Then that is correct also. Okay? So you will see that if I have like 2 packets, then it will arrive at time 20. If I extend it down to 800 packets, then this will arrive at time 4010. So you can also think of it this way. This is what I think what Kuei mentions. Until the first bit is 10 milliseconds, then up to you reach the end, there is 800 times 5 also. Yeah, so both methods are correct. Thanks, Kuei. Any questions? So this is actually I think this is like the most important problem of the whole tutorial, because the next tutorials will actually be based on this assumption. Currently, we ignore propagation delay, but later on, once we have propagation delay, things might get more complicated. So try to understand question 3D first. Okay? Questions? Now, we see that if we use message segmentation, the end-to-end delay is actually quite small. 4.01 seconds, compared to if you send the whole thing as one message because of the store and forward. Okay? Now, in addition to reducing delay, what are reasons to use message segmentation?
If, if it gets corrupted, then you can just send a smaller packet instead of like the whole thing.
Exactly. So this is something you commonly see. You download like 5 GB of item, right? If one error occurs, you re-download things, right? So if there's like some bit errors that occur, then you don't have to resend the whole thing. So that's one thing. Anything else? Those who haven't spoken? Anything else?
Message security, if anybody intercepts your message, then maybe like they can't figure out the entire thing.
Only if the message goes into different routes.
Load balancing.
Load balancing can come also, yes. Might be load balancing, yes. Because yeah, I think that is also part. Because if you have like say for example smaller packets that you send, right, then likely the router would be able to accommodate. Because router also have their own buffer, right? If you exceed this buffer, then cannot be sent, right? Router cannot handle that. So yeah, load balancing also. Yeah.
What about the idea of like loss tolerance? Like data loss tolerance?
Loss tolerance is yeah, I think loss tolerance is actually like some extension of the first item here lah. So instead of retransmitting, then you can just discard it and it should be fine. That will be important for UDP later. Yeah. Hey, what's your name? Stefan. Sorry. Sorry guys, I might take about 4 weeks to actually understand you all. Okay. Okay, so another way also you can see, like for example, if you have message segmentation, say you have a large chunk of data, depending on how the policy of your queuing is, you can have like some other items interleaving also lah. So this one will actually like try to ensure not much, right? I think in operating system we call it like some kind of a starvation item lah. Okay, so you don't want to allow one whole thing to be occupied just by one whole chunk lah. Okay, compared to for example if you don't use message segmentation, you send a huge 3 hours video, this will be occupied. Okay, so depends on how you schedule the policy of your scheduling. Okay, now message segmentation is good. It reduces the end-to-end delay. But is there any drawbacks of using it?
Manage the order.
Exactly, manage to order. Because if you have like separate items, they might not go in just one single route. So they can take, for example, different routes, say for example from here to New York, right? It can go through directly under the ocean, or for example, you can go through the land through Europe, right? These are two different routing problems. Later on, you will see in the routing protocols. So order is important. Anything else?
It's larger.
Exactly. So there will be greater overhead. So each packet here is not just purely about the data. Because if you send packet just the data, right, without any additional items, any additional identifier, right, then how do you know if this packet belongs to who? Back again, this is a system of just bits, okay, 101010. So you will have to put some kind of additional metadata lah. The ID, where this packet belongs to, where to go. Okay, so each packet will actually have their own packet headers, which we will discuss later. Then that will give you more overhead. Okay? Any questions? If not, we move on to the last part. This one is quite fast. So suppose you want to connect n devices. There can be a link between there can be either 0 and 1 link between any two devices. What is the minimum number of links?
N minus 1.
N minus 1? Why is it n minus 1? Oh, how is it n minus 1? Sorry, not why. How is it n minus 1? Any single topology you can give?
You can connect N to 1 and connect point.
Okay, so something like you can do this lah. Okay? Or you can connect them all in just one single line. And what's your name? Yue? Kiwi? Okay. Okay. Anyone has any other topology that can be done with n minus 1 links? I think discuss some graph problems.
There's so many. Yeah.
Yeah. Okay. So there's something called a star topology, connecting to one single device in the middle. Another one called a chain topology, or sometimes you also call this a bus topology, just one single line. Or, I think just now some people mentioned graph things. In 3040, as you learn that a connected tree has n minus 1 edges. Okay, in 3040 you learn this. So you can have a tree topology, just branch down, this also have n minus 1 edges. Okay, as long as there's no cycles. Any questions? Now we discussed about the lowest amount of links we can have. What about the largest amount of links we can have? What's the largest number of links?
N into n minus 1 by 2.
N?
N into n minus 1 by 2.
Okay, yeah. So that would be n times n minus 1 over 2. How did you get this?
So every device you divide by 2 because you're overcounting it by 2, right?
Yeah. So say for example you have 5 items. Each node will be connected to 4 separate links, right? So that's like n minus 1 links. This will also be connected to 4 separate links. So all of this would account to n times n minus 1. However, a link between this node to this node is the same thing as the link between this node and this node. So we double counted. Divide this by 2. Then you get. Okay? That's the first idea of thinking it. Another way you can see, right, from this node, you have 4 links, so n minus 1. From this node, this one has already been created. So just need to add 3 links. So this will be n minus 2. This one just need to add 2 links. There's n minus 3. This one just need to add 1 link. And 1 link here. So that will be n minus 4. So n minus 1 plus n minus 2 plus n minus 3 plus n minus 4. This will also give the result. All the way up to 1. This is an arithmetic sequence. Another way again to think of it, right? You have n nodes, you choose 2. This is basically the result. It's a combination problem. It's called the handshake theorem, if I'm not wrong. Okay? So yeah, it's n times n minus 1 over 2 links. How do you do this? This is basically what we call the mesh topology, which forms a complete graph. Okay? Now, those who haven't participated, please share your answers here. What are the pros and cons of using the network topologies in A and B? So let's discuss about the minimal number of links first. What are the advantages? What are the consequences?
It's easier to set.
Easier to set up, yes? Anything more?
Maybe it's cheaper.
It's cheaper, correct?
If you daisy chain, then you cannot manage as well.
Hmm?
If you daisy chain, then you cannot manage as well.
If you...
daisy chain, the bus topology. If you use bus topology, then you don't have like a switch in the middle. Then management, you cannot manage the power.
Okay. So then it will be more like peer-to-peer managed in a sense.
Yeah.
That would be for the bus topology. Anything more? Any consequences? This one is easy, I think. Any drawbacks of using bus or star?
You wait.
Okay, wait longer. Say if you sway, you start from one end, you have 10,000 nodes in middle, right? To pass it, you have to pass 10,000 different items, right? Okay, any more? So say for example these links, right? What happens if one of them break? Can this connect with this? No. Can this connect to this? No. In fact, this happened before. If you have seen the news, there was one time that sharks ate the wires between 2 oceans. This actually happened. Okay? So yeah, it's cheaper, but it's prone to a single point of failure and also hard to... it's longer parts. Last one. For those who haven't participated, this is 3 points. Pros and cons of using mesh topology. Those who haven't spoken? Can just flip everything in A. Yeah, Sidan, Derek, Xavier O. Okay? Fastest connection? Okay. Then if one link breaks, it still has a backup lah. Okay? So it's not prone to a single point of failure, but it costs more. Okay? So yeah, any questions so far? If not, then that is it for this tutorial. If I haven't caught your name, please let me know. Otherwise, don't forget the assignment 0 is next week. Okay? I think so far I haven't, the only person I haven't marked is called James, Ivor Chua, and Shi Kwan. If you are between these, can let me know. Huh? Okay. Other than that, thank you for coming. I'll send the slides later.
I was talking about